I won't say atomic, because that carries the idea that you can't cut it. And everything we said you couldn't cut, it turns out you can cut. So I'm going to stop using that word. There are modules, units, and they're made up of smaller modules, and we don't know where that ends yet. The emphasis, the beauty and importance of modular architecture was pointed out in a beautiful paper by Herbert Simon called The Architecture of Complexity, back in the 1960s. And I think it's relevant for problems today. Quantization was born as a way of getting finite answers from infinite theories. It began with Planck arbitrarily putting in quanta of energy, depending on the frequency, for his oscillators, in order to get a finite heat capacity for ovens. And if you look carefully, every quantization since then has been a way of resolving continua into quanta. Quanta are strange creatures. You can count them, but you can't describe them completely. If you look at one of their properties, you can get it precisely as you like. But for each property you look at, there's another one which is disturbed by measuring the first. So you can't add up all your measurements and one coherent picture. This fact that in an atomic world, measurement, exact measurement, complete measurement is impossible, was actually put forward by Democritus, one of the early atomists. If you have a world made of atoms, he said, you see it by it launching some of its atoms to you and having them produce changes in you. And he had an intuitive feel for action and reaction. The change in the body required to launch a signal must be somehow comparable to the change in you that it produces on receiving it. So all the news you get is automatically out of date. The process of sending it out changes what you're looking at. What is actually going on is that a change in the body results in a change in you. There's a transmission of changes, not of information about what the body is, actually. The whole idea of what a thing is becomes rather meaningless if you can't see it. It's a mental construct that you can't really count on. And I think that for students of quantum theory, real should be regarded as a four-letter word. This is shown up. This shows up in Heisenberg's theory as non-commutativity. The things that deep down don't commute are ultimately acts of perception. Looking at this and looking at that, you get answers which depend on the order. Heisenberg didn't have this interpretation at first. He started with things like the Poisson bracket of classical mechanics, which is 1 for P and Q, and -1 for Q and P. So there's a built-in non-commutativity in classical mechanics, which Heisenberg, after a great struggle, recognized as a relic of a deeper non-commutativity in quantum theory. In the classical physics, you still had a commutative product. If you just multiply Q and P, the order doesn't matter. And in quantum theory, it matters, and the Poisson bracket is just a little bit of a correction that's left in the classical theory if you don't stop with a zeroth order correction. So I take it through. I'm spending a lot of time on basic principles because I don't have good experimental results. I don't have important predictions. I've really nothing else to go on but to try and do what has worked in the past and hope it will work again. I'm convinced that you have to dissect space-time into its modules in order to make sense of the central singularity of the black hole. And I have to follow the saying of Julian Schwinger, the next theory grows out of the most advanced form of the old theory. And the most advanced form of what goes on in the school that we have today is not general relativity, which works with astronomical observations mostly. It's obviously the standard model, which is formulated in an action principle. So even though I was led into the problem by trying to understand general relativity, I think this is a problem which cannot be solved on the level where it's posed. And what I'll put forward today is a proposal for its solution 6 levels down. I'm going to show you a 6-story building, and general relativity is on the 6th story, and we're going to be monkeying around on actually 7-story building. There are 6 stairways, six levels of rank, promotions that we have to go through. But we'll start with rank 0. Okay, the basic idea of quantization is a resolution into quanta. It didn't look that way at first. When you quantize a harmonic oscillator, you think you're just finding the position, or let's say the energy, has discrete values. But after a little experience in field theory, it was realized you could say the oscillator itself was a collection of things called phonons. You have either none of them, or one of them, or 2 of them. And the operators that we call P and Q, the momentum and coordinates of the oscillator, are actually convenient linear combinations of the operators that create and annihilate the phonons. I always get the sign wrong. There are only two possibilities. Either Q plus IP is the annihilator or it's the creator, and this is the other one. And their Poisson bracket, if you call this A and A star, I'm guessing that this is the annihilator. If you work out the Poisson bracket, you get that A star on A is, I guess, I or something like that. If you work out the commutator in quantum physics, you get 1, aside from, you have to get the units of H bar in there and so on. I'll take supernatural units where everything is 1. Okay, then this theory of creation and annihilation was actually the first statistics discovered. Bose realized that Einstein's photons had to obey this statistics to get the results that Planck wanted for the specific heat of the radiation in an oven. And then along comes the atom, a few years after Planck. And you have the problem of why the electrons in the second shell of the lithium don't fall down into the first shell, where there are already 2 electrons waiting. And Pauli inferred from atomic structure that there's an exclusion principle. 2 electrons can't have the same properties. Now there's an earlier theory of the exclusion principle. It's called set theory. A set either contains an element once, or it doesn't, which is like containing it 0 times, and it can't contain it twice. That's considered meaningless. So if you have an annihilator of an object, and if A star is the creator of the object, then in order to annihilate and then create, it has to be there to begin with. So this is 1, gives you back to the original thing, if the object is present, and 0 if it isn't. And by the same argument, A star is 0 if the thing is present, because you can't create it by the exclusion principle of classical set theory. And if it's not there, then you create and annihilate again, and you get 1. And you add these up, and you get A star plus A star A equals 1, which is the statistics of classical set theory. So a quantum set, a Fermi-Dirac symbol is only the quantum version of what Peano and Cantor call a set. The Fermi-Dirac symbol can be called a quantum set. That makes it seem pretty fundamental. Where do these things come from? Well, after a few decades went by, Tominaga showed that if you have a lot of fermions and they pair up, that fluctuations in the gas of fermions behave like phonons, and they obey an approximation to Bose-Einstein statistics. So if you have Fermi-Dirac, you can build Bose-Einstein. Maybe you can do the other, but there's a big difference. Namely, there are just two possibilities here. And with Bose-Einstein, you have an infinite number of possibilities. There can be 1 quantum, 2, 3, 4, 5. So Bose-Einstein theories lead to infinity, or rather start from infinity. Whereas set theory starts from binary possibilities. Either it's there or it's not. And all the infinities of classical, of quantum and classical radiation theory come from the Bose-Einstein statistics that the phonons obey. And by the way, that apparently the elements of space-time seem to obey if you believe the Heisenberg commutation relations for momentum and position. So, if I could make contact with my starting point, to get rid of this damn singularity, you somehow have to build the world out of fermions, out of things with these statistics are called odd, and these statistics are called even, because two of those make one of those. Well, there's then one process. Every quantum system has a space in which you find its input modes, called kets. Now, I'll call that the mode space V. Sometimes they're called state vectors. That's a very confusing name, because state implies you can know everything about the system. And you can know everything about the state vector and know very, very little about the system. So I call them modes. One of my teachers, Weisskopf, called them channels, which is perfectly good. It indicates that quantum theory is about the operations you carry out in the laboratory, not about ideal states of knowledge gotten by divine intervention. So, to go from the modes of an individual to the modes of a set of those individuals, in classical thought, you form something called a power set, which I'll write this way. This is a kind of multiplication sign. It's a big wedge, not the letter lambda. And another way of writing this in classical set theory is 2 to the v, because it's called the power set. And the reason for writing it that way is the number of things in it is 2 to the number of things in v. If you have a set of n things, the number of sets of those things is gotten by making a binary decision to be or not to be for each of the n things. And there are 2 to the n possibilities, therefore. Okay. And all these equations work in the quantum theory, too. The only new thing is that you have this operation of coherent superposition, quantum superposition, that classical set theory doesn't know about. You get the Fermi statistics from, or odd statistics from classical set theory, but just by turning on quantum superposition. To make a modular architecture, you can't stop. You can't just have one. You can do it twice. And that will give you 2 to the 2 to the v possibilities. And for short, I'll write that. I'll read this as Grassmann. Grassmann was an interesting mathematician, physicist, linguist, you name it. In 1864, he discovered Grassmann algebra. In 1860, roughly, he invented the idea of linear algebra and the idea of vector space. Okay, so what I'm doing here is just iterating the process of the power set as often as you need to do physics, and then stop. And the numbers go up pretty quickly. If you start from 0, 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 4 is 16, 2 to the 16, as everyone knows, is 65,536. And next comes 2 to the 65,536. People have guessed that there's something like 10 to the 80 particles in the universe. 10 to the 80 is like 2 to the 240. You triple the exponent roughly to go from powers of 10 to powers of 2. And this is humongously bigger than 2 to the 140, what have you. This is certainly too small for field theory. It's not that hard to see that there are more points than this in the universe. This is very likely too large for field theory. It's very unlikely that you'll ever have to go beyond this. You might want to just to make things more elegant, but then most of the space you get you won't use, just as most of the sets in the universe are sets we don't come near in physics. So I'm going to suppose that 6 quantifications is all are allowed. And now, does this have anything to do with the world? This is all words, symbols. And so you look at the elementary particles, and you know that depending on how you count, you could say there are 8 fermions. I mean fundamental fermions of the first generation. Generation is a problem I don't understand. I won't talk about it here, unless you make me. And so I'll just look at the first generation for now. And in the usual way of counting, there's an electron. Yes, it's both right-handed and left-handed. It has both particle and antiparticle, and a spin up or spin down, and it can be anywhere in the universe. And I count all that as 1. And then there's neutrino, which has just as many possibilities nowadays. A decade or so ago, before the oscillations in the neutrino beam from the sun were measured, it was thought there was only a left-handed neutrino. We still haven't really seen the right-handed neutrino, but we've seen things that would be explained if there were one. It's not trivial, it's not crazy to assume it's there. So we have both right-handed and left-handed neutrinos, which like we have an ambidextrous neutrino, just as we have an ambidextrous electron. And then for each of these, there are 3 quarks. It's customary to call this the up lepton and this the down lepton to get them into the same algebra. And the up lepton has up red, up green, and up blue quark. And the down lepton has a down red, down green, and down blue quark. And each of these has as many other variables as these do. But we're counting these as 1, so we can count these as 1. It's as if the fermion consists of a bare fermion that has all the other stuff. And attached to it is a codon, which has these 8 possibilities. Instead of talking about codons, I'll use a term that psychologists have started using lately. The things that combine to make a particle, which are not particles, but properties of particles, can be called qualia. And spin, I'm not putting a particle together out of particles, but I'm putting it out of qualia, like spin, isospin, color, generation, and up here is position. There are 3 generations, 3 colors, 2 isospins. Counting spins, you have to choose, you want to count the work count in the relativistic way or the pre-relativistic way. If you talk about Pauli-Kind spin, it's up or down. If it's Dirac spin, there's a difference between positive and negative energy. For the individual electron is also there. In that case, there are 4 spins, 2 binary possibilities. And then here comes infinity, which is where all the 3's blow up. because the infinity of space-time. And these are all qualities of the fundamental fermion. And it was really a great shock for me when color was discovered. There's three possibilities. In group theoretic language, the isospin group that distinguishes these two is SU2, and the group that distinguishes these three is SU3. And 3 is not a power of 2, I believe, but check me on that. And this kind of game, was going to produce powers of 2 galore. But if you actually look at it, there's exactly one case in this whole line where going from one level to the next triples the population, the number of possibilities. And that's here. 16 is 4 plus, this is a nest, so each of these includes everything before it. What's excessive here is 12. And that 12 is indeed 3 times 4. So the immediate hypothesis is that leptons occur when this extra standard model qualia is, this is rank 0, 1, 2, 3, 4. Rank 3. Yes. No. That's right. Two squared is 4, and 2 to the 4 is 16. This is rank 4. Okay. So the suggestion is that as the lepton arise from rank 2, the general fermion is rank 3, and color is just the part of rank 3 which is not rank 2, which I call proper rank 3. The story is a little bit richer than that. Not much, but a little bit. Namely, the 4 possibilities for isospin let me see, there are 2 for this and 2 for this, making a total of 4. In gut, the grand unified theory, Georgi observed that the combinations of isospins that you see in the lepton are best described by a binomial formula. This is exactly what you would have if you have a set of elements, each of which is binary, has 2 possibilities. This is the case where they're the same, where there's only one. This is the case where there's only one of them. And here are 2 possibilities. And this is a case where there are none of them. That's just 1 possibilities. And this is the case where there are 2. In that case, by the odd statistic, they have to be different. So there's only 1 possibility. So the process of power setting is actually carried out several times already in gravity-of-light theory. And we can just take this part of GUT over into this step theory. Now there's one difference in goal. GUT was an attempt to unify the particles. And this construction does not lead to simple groups. It doesn't lead to unification. On the contrary, it gives semi-simple groups which have lots of parts to them, like here. It's not proposed that the basic dynamics have this 16-dimensional symmetry that this space has, for example. I'm not in the least trying to unify anything. I don't think the world is simple. Rather, I'm just trying to make a theory that makes sense at every stage of the calculation. So if it's wrong, you can find out, instead of having some divergent integral to scratch your head over. Once you have a theory that gives answers, then you can work with it, correct it. Okay, now, it turns out, curiously, that this binomial structure also works for color. The 6 possibilities you see here are just part of the power set of a set of 3 possibilities. These are not colors in the usual sense. They're one step down, call it pre-color. And this isn't isospin in the usual sense. It's one step down, call it pre-isospin. One of the things you have to worry about is the fact that Grassmann worked with real numbers. Grassmann algebras are real. Quantum theory worked with complex numbers. And the Grassmann algebra over complex space is not the same thing as the Grassmann algebra over that space regarded as a real space. So there's a decision that had to be made. There's a big difference in dimension. This question already came up, however, in the first really interesting attempt to quantize space-time, which was, well, the second. Let me mention 2 earlier attempts from which I learned really important things. The earliest was by Feynman. The earliest significant one, that is. Feynman knew the Dirac equation, and knew that Dirac had invented this vector gamma mu, whose physical meaning was obscure from the start. It gave beautiful answers, and 2 gammas make a spin, but it's not clear what gamma itself means physically. And what Feynman did was imagine that these gammas are quanta of space-time. And when you see a coordinate x mu, it's actually the sum of the gamma mu's of a whole host of spins. And this guarantees that the Lorentz invariance that Dirac had carefully developed for his spins is inherited by space-time, which is a big problem if you're trying to break space-time into things. Any kind of a crystal lattice immediately breaks relativity. This at least saves the Lorentz group. You still have a little problem with translation. And the next important development by Yang in 1947 took care of translation. Yang was building on, where am I on the clock? I guess I can talk for 2 minutes longer, right?
Mm-hmm. Yeah, absolutely.
Okay. Just getting to the good stuff. Yang, the theory of quantizing space-time goes back at least to Heisenberg. Very soon after he quantized the hydrogen atom, he saw all the infinities floating around and thought that space-time should be quantized. And he suggested this to several people, in particular Oppenheimer was studying there. And Oppenheimer transmitted the idea to Snyder. And Snyder published one of the earliest printed papers on quantized space-time, in which x and p don't commute. The commutator of them is an angular momentum. His commutation relations were real asymmetric, odd, didn't make any sense. And Yang was a graduate student at the time, and he pointed out that the whole thing becomes very pretty and, in fact, simple if you add two dimensions, which I'll call the Yang dimensions, in order to represent I as a component of angular momentum of the whole system. And if you call the usual dimensions 1, 2, 3, 4, I is the component of angular momentum in the 5, 6 plane. So it commutes with all of them the way it should. And then I put here a sum to indicate that you sum over a lot of things. I wouldn't even bother writing down the commutation relations for L, because they're those of an angular momentum. They're absolutely standard. Mathematicians have known them for a century. And the important thing is a dictionary. X mu is the sum of all these components. And P mu is the sum of all these components. So it's a block structure. In which, let's say, X is here, and P is there, and L is there, and I is there. And Yang didn't push this very hard. He wrote 2 papers and then got out of the field. But he pointed out that in order to get back to standard quantum theory, you have to make this commute with everything. That's like going to a classical limit for this variable. And that always implies some kind of coherent organization. So already in Yang's paper is the implication that space-time is something like a superconductor or a ferromagnet, where all these huge number, like 10 to the 80, of components of angular momentum coherently organize and fix one dimension, which is what we call the I of quantum theory. And these are what's left over, corresponding very small vibrations of the angular momentum about its permanent magnetization direction. I could go on like this for quite a while. In order to even approach gravity, you have to make a theory of the gauge fields. And almost as soon as quantum theory was born, it was suggested by de Broglie that the photon is a pair of neutrinos, which is a way of understanding why they both have mass 0. And this idea that they're having 0 mass is related was ultimately parlayed into supersymmetry. It quickly became pretty clear that a neutrino is not a pair of, a photon is not a pair of neutrinos. The Heisenberg uncertainty principle tells you that to keep two neutrinos together to make them imitate a photon, in order to have a small relative position, you have to have a huge relative momentum. So they're rattling back and forth like mad, which implies very, very strong local binding forces between neutrinos. And the weak interactions aren't like that. And even the strong interactions have asymptotic freedom. So the canonical quantum theory quickly shot down the 2 fermion theory neutrinos, and Feynman shot down the similar theory for gravitons. They're not 4 neutrinos either. But these variables only obey the Heisenberg uncertainty relations when you're looking at really large numbers of spins. And when this polarization that makes the I commutative is valid, if you go into very small distances, you disturb the organization of space-time, and you'll go back from Heisenberg's uncertainty relations to the angular momentum uncertainty relations. And that doesn't prevent you from knowing two components of angular momentum, because the commutators of angular momentum are themselves. They can all be zero. In that case, you can know all components exactly. They're all zero. In fact, that's the only case. You can know them all exactly. But you can know them pretty well if they're small. And this is the opposite of the behavior of the Heisenberg uncertainty relations, where making one thing small makes the others big. So the old arguments against the pair theory of the gauge fields are no longer valid. And it's very easy to write formulas that have the right transformation laws for the gauge vectors. Gradually we're reaching the point which I was hoping for when I began, of being able to make stick figures for the histories of fermions the way organic chemists make stick figures for the benzene ring. That doesn't mean you'll know everything about it. That's quantum theory. You can't know everything. But you know some important things about benzene when you discover the ring. I'm looking forward to what we discover about the fermions when we discover their skeletons. Okay, thank you. I've explained everything very carefully. There can't be any questions.
Have you ever touched on the Yang-Mills problem for the gauge fields?
Well, since I don't believe in the continuum, I have to regard the Yang-Mills theory as an approximation. Most of the problems with it are infinities. And this is a wholesale solution of all the infinities. So don't worry too much about renormalization. All these renormalizations are going to be finite. Renormalization is a physical effect, like the shielding of a charge in a plasma. And it's going to be here too, but I'll probably get the wrong answer, but at least I'll get an answer.
What is Wolfgang Pauli like in person?
Well, first of all, it's almost impossible for my young and tender ears to understand what he's saying. And he has an accent and a low voice besides. And when he visited MIT, where I was a graduate student, the lecture room was so flooded that I couldn't bear to sit through the lecture. So I never really contacted Pauli. But my thesis advisor was his colleague, Felix Villores. So I got some impressions of Pauli and him. And he was very creative, but also a very harsh critic. If he put a notch on his rifle for every Nobel Prize he killed, he would probably be the winner in that competition. Fortunately, he was out of town when Uhlenbeck and Gautzman came up with their theory of spin. It got published before I got back, so they got their Nobel Prize.
So, I think way back when, in the land before time, you and a colleague investigated ball lightning. I was kind of curious if you could maybe just talk about that a little bit, because it just seems a giant leap from where you ended up going later on.
Not at all. First of all, I was working in the plasma energy program, thermonuclear program. And I think it was Shafranov put forward the idea that ball lightning was a natural, self-confined hydromagnetic structure. Nowadays, we call such a thing a soliton of the electromagnetic and conduction field of the plasma. And I saw that the virial theorem of fluid dynamics had a relativistic form, which excluded the possibility that some collection of currents could result in a surface pressure less than what you'd expect from the energy inside. It could, in other words, it couldn't hold itself together for longer than it takes light to travel across the diameter. And so that raised the question of what it was. And I couldn't resist speculating that in fact it was a kind of soliton in the Earth's electric field. You have this variable conductivity. Cold air is not very conducting. The minute it breaks down, it becomes a readable conductor. And then that focuses the electric field there to continue its breaking down. So you can have something that's self-confined by the nonlinear character of conductivity. This is sort of antithetical to Kapitz's idea that you have microwaves coming down to the lightning channel from above. But that also indicates how it's probably wrong. Namely, it was a DC theory. And we have a breakdown in air. Undoubtedly, you have high-frequency oscillations. So the whole theory has to be done over again in microwaves. In fact, I'm in touch with a couple of Russians. Russians seem to have a love for the lightning. They have taken into account the oscillatory character of the discharge. And this idea that all lightning is a soliton is working out. After all, I got into this game, this central singularity, by discovering a soliton in the gravitational field, and which I call the kink. And that's what made me realize that you could have a solution which is stationary but cannot be made static. Because the kink has this rotating light cone, which distinguishes the past from the future. And that even led me to speculate that particles might be mini black holes with the T violation coming from this property of the gravitational field. Nowadays, I think that's a crazy idea. The numbers are just out of reason. Did I answer your question?
Yes.
Okay.
Do you have any personal stories of physicists that we know as legendary today that you could share with us?
No.
Do you have any that you have, you're just not willing to share? Can we come ask you those in private, maybe?
I have to know you for quite a few years.
So there's a chance.
In the quantum world, everything is possible.
In terms of your effort to make sort of algebraic theory that makes sense, what are your biggest challenges that you've been
Another good question. And I don't know the answer. Everything I've talked about today, except for circulations, has been kinematics, getting the algebra right. The real core of the problem is getting the dynamics right. I don't see how you can predict much. The uncertainty relation helps. That's something you can measure. You can verify that Heisenberg's uncertainty principle is wrong at very, very high energies. And the breakdown would tell you something about the size of what I call a chronon. But the real problem is to write down a plausible dynamic to the whole world of possibilities. And what I'm doing actually is looking at the standard model Lagrangian. And I know pretty much what to do for the fermions in it. And I have a guess about what to do for the gauge ions in it, namely pairs of fermions. And I only use one little outlier. I'm not quite sure of how to express the Higgs in this language. That's my main. You see, there are lots and lots of questions, but that's the main big one right now. How did Higgs fit in? But in earlier work on quaternion quantum theory, the Higgs effect of getting masses out of the gauge theory came just from the eye not being central, but being variable. And that's what we have here too. So I'm almost embarrassed to suggest it. But I'm hoping that that A, I take for granted the Higgs is a condensate, as so many people speculate, and there's a condensate here. So maybe deep down, this is the I in Higgs, as it were. There's a catch, namely this thing would seem to be a triplet, and the Higgs is a doublet. But you know, there are ways to make a triplet out of two doublets.
I'm still not sure how you're going to get, well, how you're going to build an X mu out of gammas the way that Feynman had algebraically. You said that he took and built a decision out of a product of.
Here it is. Oh, I'm sorry. Thanks for the question. Forgive me. I gave Yang's version of this,
Yes.
where these are orbital angular momenta, really, differential operators. And I gave Feynman's version, where they're spin operators, and I forgot to put them together. Mainly for, I accept Yang's formula, which for me L is the sum of gammas.
Okay.
There are two indices, which I'll call Yang indices. The group in question is spin 3, 3, which has to come out of this 3. And
So is that a direct
so it's
product?
just a
of
bunch
spin
of direct
three?
operators.
What do you mean by spin 3, comma 3? Is that a direct product of two SU3s, or is that?
No, what Yang suggested is that somewhat deeper than space-time, there's a six-dimensional world in which the metric has 3 positive signs and 3 negative signs.
Oh, okay.
This thing obviously includes Lorentz,
Yeah.
and that's what it does. This, for Yang, this is the Lorentz group. The subgroup is this. And what's left over is little spin 2, which is the I.
Right. Well, wait.
No infinities. That's big numbers.
If no one else has any other questions, I guess I got a final one. What advice would you have for a group of undergraduates who are just now getting into physics as a profession?
Solid state. Condensed matter.
in this now?
First of all the important ideas come from there nowadays. I guess general relativity didn't, but everything since the beginning of quantum theory has. And it will sharpen your intuition for field theory, for the hard problems, and keep you off the street corners of string theory and supersymmetry. And all those addictions.
That question actually led me to think of another one. Recently I read an article about how, because of all the large data that we're needing to process, we might need to come up with some new form of mathematics that would be, to quote the author of that particular article, would be as pivotal as when calculus was invented. Do you think that holds any sway?
You know, physicists invent new forms of mathematics as part of their breakfast. That's no big deal. And yes, it would be nice to have that, and it's going to happen. But probably by someone closer to your age than mine.